Alright, hello students, welcome back to another lab for ComSci 191, Computer and Network Security. So in this lab we're going to look into public key encryption. So the public key encryption was initially introduced by Diffie and Hellman in 1976, and this is based on mathematical functions rather than simple operations on bit patterns. Recall that in the symmetric encryption topic, we have transformations and substitutions, basically based on the bit patterns. But the one introduced by Diffie and Hellman relies on mathematical properties. And public key encryption actually uses two separate keys. That's why it's often called asymmetric encryption. Now, before proceeding, let's talk about, or let's address some of the misconceptions about asymmetric encryption. The first misconception is that asymmetric encryption is more secure than symmetric encryption. So this is false. Okay, recall that the properties of a good encryption algorithm is dependent on many factors, and one of them is the encryption algorithm and the key size. Right? So an encryption algorithm can be attacked by cryptanalysis, by analyzing the algorithm, or it can be done by a brute force attack, by trying out all possible keys. So it doesn't actually make this asymmetric approach more secure, even though there are two keys. The second one is it has made symmetric encryption obsolete, which is also false. Okay? This does not mean that we have asymmetric encryption. We no longer need symmetric encryption. Okay? One of the key difference between asymmetric and symmetric is that asymmetric actually takes longer to perform the encryption. So in some applications, symmetric encryption is preferred over asymmetric encryption. Third misconception, easier key distribution than symmetric encryption, which is also false. Remember that in the symmetric encryption, there should be a shared key between the sender and the receiver. And in asymmetric, we have a public key and a private key. So can we assume that the key distribution is easier? So it's not the case also. Actually, your lab today will talk about PKI, which has something to do with the key distribution. Okay. So these are the elements of the public key encryption. First, you have the plain text input, and that plain text will be inputted to an encryption algorithm, say RSA. Now, this is to address confidentiality. Right? So what we're saying here is Bob would like to send something to Alice. Okay? So Bob will need to obtain the public key of Alice from Bob's keyring. So in public key encryption, you usually have a keyring that contains the public keys that you have added to your keyring. So in this scenario, Bob has a keyring with several public keys from his friends, for example, and including the public key of Alice. So if Bob wants to send something to Alice, what Bob does is to get the public key of Alice, which is PU sub A. This will be the key used in the encryption algorithm with the plain text and the public key, and you will get the ciphertext. Essentially, the encryption algorithm will have the public key of Alice and the message, and this will be transmitted to Alice. Now, on Alice's end, she will receive the message, the ciphertext Y, and she will run it on. She will use the decryption algorithm. If RSA was used at the sender end, it will also use RSA here, and then instead of using the public key for decryption, Alice will decrypt using her private key. So as you can see, to retrieve the plain text, we run the decryption algorithm using the private key of Alice and the ciphertext, and thus we get the plain text output. So the essence here is there are two keys, the private key and the public key, and on Bob's side he used the public key of Alice to encrypt the data, and on Alice's end she used her private key to decrypt the ciphertext. Public key encryption has the property that only the private key can be used to decrypt the ciphertext encrypted with the corresponding public key. So remember that when you're using public key encryption, you always generate two keys, the private key and the public key. You can also use public key or symmetric encryption, okay, not encryption, but for authentication. Okay? So the first one is for confidentiality. Okay? You would like to protect the data so that nobody else can see the data. For authentication, you would like to verify whether the ciphertext or the message that you are receiving really came from the individual who claims that he's the one or she's the one who sent the data. So in this context, it's almost the same as the other one. So here we have Bob. Okay? So the scenario here is Alice would like to make sure that the message she receives really came from Bob. So to prove that, what Bob does is to get a plain text input, Bob will encrypt that plain text input with his private key. And that encrypted ciphertext, so take note that the key used for encryption here is the private key. It will be transmitted to Alice, and Alice will decrypt the ciphertext using Bob's public key. And if she's able to decrypt the ciphertext using Bob's public key, then Alice is sure that indeed the message came from Bob. So that's the idea of authentication using public key system. You encrypt your data with your private key, and the receiver will decrypt it with your public key. If that message is decrypted, then the message is authentic. Okay, so we move on to the next one. So applications for public key crypto systems. So we have several applications. First, we have digital signature. Second, symmetric key distribution. And third, encryption of keys. So we'll talk about digital signature later. Okay, we'll discuss this one by one. So we have four common algorithms. We have RSA, we have Diffie-Hellman, we have digital signature standard, and we have elliptic curve cryptography. And it's a table that indicates whether the algorithm can be used for digital signature, symmetric distribution, and encryption of secret keys. So notice that the RSA is the one that can be used for all of these applications. Diffie-Hellman is used for symmetric key distribution. Digital signature, we have DSS, we also elliptic curve cryptography. Okay, so two RSA and elliptic curve. So what are some of the requirements for public key cryptography? So we have 6 requirements here. The first one, it should be computationally easy to create key pairs for Bob. Okay, so you have public key and private key. So usually most tools will have a keygen program that will generate these 2 keys. It's computationally easy for sender A, knowing public key, to encrypt messages. So that means that it's easy to perform encryption. So using the public key and the message, you get the ciphertext. Third, it should be computationally easy for receiver B, knowing the private key, to decrypt the ciphertext. So in this case, we have the ciphertext encrypted with the public key, and then the receiver should be able to decrypt that, the C here, with his private key B, which is actually equal to this. So we can just substitute this one with this. It should be easy, computationally easy to do that. Fourth, computationally infeasible for opponent to determine the private key from the public key. So remember that the public key is distributed to the public. Given the public key, it should be very or impossible or actually infeasible to derive the private key. So even though you have the public key, you cannot get the private key by just analyzing the public key. Fifth, it should be computationally infeasible for the opponent to otherwise recover the original message M given C and the public key. So given the ciphertext and the public key, M cannot be derived from that. And it's also useful if either key can be used for both encryption and decryption. So here we have M equals the public key, encryption, private, using the private key and the message, or same process, we get the same message, PRBE pub M. So it's just the reverse. So we have 4 algorithms, RSA, developed in 1977, only widely accepted key encryption algorithm, and needs 1024 plus bit keys. Then we have Diffie-Hellman key exchange algorithm, which allows the exchange of secret key. We have the digital signature standard and elliptic curve cryptography. So the main characteristics of elliptic curve cryptography is smaller keys. So application for public key algorithms, we have digital signatures for authentication. So we have the hash value. Example, using SHA-5112, our message is encrypted with a private key. So we discussed this in the previous lab when we talked about message authentication code, wherein we can use private key encryption, symmetric encryption, asymmetric, and key map. Then key management distribution. So this is actually the problem for the lab that you're going to work on. Public announcement of the public key can be forged, okay? And there should be a secure distribution of public keys using certificates. And as I said a while ago, usually symmetric and asymmetric are used together. So the public key algorithm can be used to distribute secret keys for private key encryption, and can also be used to create temporary keys for message encryption called a digital envelope. Okay, so this figure, I'd like to emphasize that this is the main figure that you're going to use to understand your lab for today. So public key certificates. So the idea of having certificate is having somebody to certify for you that indeed you are the true owner of the information that you claim to have. Right? So let's say you are Bob. So we have Bob here. So Bob has information about himself, and Bob has a public key. So again, the distribution of the public key can be forged. Okay. So what is going to happen is that Bob will have to ask some trusted individual to sign this certificate to verify that indeed he is the person he is claiming to be. So we have an unsigned certificate, which contains the user ID and the public key, as well as the information of the CA. CA is called a certificate authority. So what will happen is Bob will generate what you call a certificate signing request. Okay. So this data here will be fed to a hash function which will generate this hash. Okay. And then in order to sign this certificate, the certificate authority will encrypt the generated hash, okay, with the private key of the certificate authority. Okay, and that encrypted hash code will be added as part of the certificate. So this is the full certificate. So if anyone would like to verify that indeed you are the owner of the key, then it can easily be verified. So this is done by the certificate authority. Then at the receiver end, so the receiver would like to verify whether it is indeed Bob's public key. What will happen is it will extract the information and then get the hash of that. So we have this block of data, and then the verifier would decrypt the attached signature to get the hash of the data, and then it can be compared, and thus the verifier can know whether this public key is indeed authentic. Okay, and the format here is called X509 standard. Okay, so that's the idea. Certificates are used to make sure that you indeed are the owner of the public key. We also have digital envelopes. Okay. So digital envelopes is very similar to this one. So what it does is you have a message, okay, and then you have a random symmetric key. So the idea here is you're going to use a temporary symmetric key that you will use for a session, a single session, and you would like to send that symmetric key to the other end. So this is similar to the Diffie-Hellman. But the idea here is you have the message and you have a random symmetric key that you're going to use to encrypt this message, and you now have an encrypted message. And then what you're going to do is to encrypt the symmetric key you used to encrypt the message using the receiver's public key. So this will be the encrypted symmetric key, and then together you have a digital envelope which you can send to the receiver. Now at the receiver end, the envelope will be open and you will get the encrypted message and the encrypted key, symmetric key. So you decrypt the encrypted symmetric key with the private key, so you get the key, and then you use that key to decrypt the message. So in a way, there's a two-level encryption that happens here. You use the public key algorithm to encrypt the symmetric key, right? So that's the idea. Okay, so succeeding topics will talk about random and pseudo-random numbers. So remember that in cryptography, we need to use random numbers, okay, for key generation, for initialization vector values. So we need to the system should be able to generate numbers. So we have these uses, so keys, session keys, key distribution, etc., etc. So random numbers are very important. Requirements are the following. So it should be random, so it should be uniformly distributed, meaning each value will have equal chance of being used, right? Unpredictability, successive values not related to previous values, okay? Clearly true for truly random numbers. But in the computer, we have what we call a pseudo-random number generator. Pseudo-random numbers versus random numbers. So it's often used algorithms to generate pseudo-random numbers which satisfy some tests. And true random numbers actually are generated from non-deterministic sources like radiation, lava lamps, etc. So those are true random numbers, number generators. Practical applications of encryption. So it's commonly used to encrypt transmitted data. So we have HTTPS, which uses TLS. Okay. Much less common for stored data, copied, backed up, and recovered. And we have different approaches to encrypt stored data. In my case, for example, I usually encrypt my home partition in Linux so that if ever my laptop is stolen, the data stored on my laptop cannot be retrieved by the thief who stole my laptop. So you can do that whenever you buy a new machine, a new computer, or you reinstall an operating system. It's a good practice to encrypt your file system. Okay, so those are the introductory topics about cryptography, symmetric and asymmetric cryptography. We'll continue on the next video.